Yes. I already know that. But yeah, it's just, yeah, it's important, but
Okay.
I mean, I used it myself, so I have
So, are there any questions? Well, as you are thinking, maybe, oh, okay.
Do you know any kind of gold standard methods for any gold standard methods for modeling, say, biological molecule interactions, such as molecular dynamics and biological molecules such as proteins?
The gold standard method. What information do you want to get at?
I guess it's proteins, amino acids of the protein when they form a chain, interact with one another.
Folding of proteins.
Folding of proteins, and also separately interactions between proteins.
So basically, so you basically want to know about the terminal structure of a protein. So you have a chain of amino acids that somehow coils up, forms some globular proteins, and you want to know how that looks like, and then how it functions basically via molecular modeling. That's the question. Well, actually, many years ago already, I talked to somebody who had about 1,000 papers related to this topic. Professor from Cornell University, Harold Sharada, and he had just introduced another method for solving this problem, protein folding. And I asked him whether everything is solved now. And well, his answer actually was a bit ambiguous, but it's certainly not all solved. The problem with this is, this is a thing where well, it's a multiple, what is called a multiple minimum problem. I mean, you have a very complicated configurational space, and say the potential energy of your protein may have many local minima in this configurational space. And maybe you want to find a global minimum. For some time, people were thinking that there is a specific meaning attached to this global minimum, and that the shape of the protein, which is later on responsible for its biological function, would be related to this global minimum. And there are approaches to finding a global minimum. We had actually a remark the other day related to this, and the remark was simulated annealing. You can use, for instance, the Monte Carlo procedure with outlining this morning to find this. So what you would do is you basically would have a chain, maybe not actually here, polyisoprene chain, but I would do as well for protein, and you make some kind of chain and change this molecule. Say, okay, I rotate this group and get a new potential energy. And is that going to be a better potential energy as the one that I had before, in the sense that it is lower? And maybe this algorithm tells us, yes, it's slower, and then you can say, okay, accept this with this given probability. You simulate at a certain temperature, and then it's supposed to be so that you spend a lot of time in areas of configurational space, a lot of time in the sense of a lot of MC steps. In the area of configurational space, where these local minima are. And presumably you spend most of the time where the global minimum is the deepest one. Yeah? The idea is that with Monte Carlo, okay, the idea is as follows. If I have a diagram like this, and say this is some kind of coordinate axis, a general coordinate. Certainly, I mean, if you have a system like a protein with many atoms in it, you can move all the atoms. You have lots of coordinates, but say, suppose you have one effective coordinate, and this would be your potential energy of your protein. Then, I mean, you look at a very complicated landscape, basically, of that, and there's somewhere a global minimum, and you say, okay, I want to look for this global minimum because if I find this global minimum, I know how the protein is folded. Yeah? And if you do this with like the Monte Carlo method I was describing, you would say, okay, I start from some place, let's say up here, this is where I start. And then the Monte Carlo method will actually kind of lead the way into this deep minimum. What you actually get from the Monte Carlo method I was outlining this morning is a frequency. So the Monte Carlo method will spend most time where, I mean, these valleys are deepest in a sense, and will spend less time when they are higher. So it kind of inverts this landscape here. And then you say, okay, there's a maximum here and it spends a lot of time here. So if I find this maximum, then I can lower myself into this pit here by lowering the temperature slowly. And then as the temperature becomes lower, I may even get a higher maximum here with a lower temperature. And everything basically falls away except for this deepest minimum, which then sticks out, and I finally find this minimum. The problem with this is, of course, proteins only function at a very specific temperature. Yeah? And so finding the global minimum may not actually be what you want to find, because the global minimum may not be, it is the minimum of the potential energy, but it's not the minimum of the free enthalpy. Yeah? You confine your protein in a very narrow potential well, and entropy may disfavor this. So the entropy may be very much restricted here, or the conformations may be very much restricted, and therefore entropy is falling, and entropy once to be as high as possible. And maybe a better maximum, a better minimum is this one here, which is broader. Yeah? This one is very narrow, but this one is broader. And so maybe it spends actually most of the time here at the temperatures, body temperature, when it's supposed where it's supposed to function. So the global minimum has a special meaning that is attached to it, which in these systems may not be, may not have actually that meaning. But aside from this question, it's sometimes interesting, even technologically, to minimize a function of very many variables. And if you do this, you can use this Monte Carlo procedure. You say, okay, I check this criterion min1 exponent minus beta delta u. Yeah. Ask the question whether this is greater or equal to this random variable. And that's the random variable from 0 and 1. And if it is, then accept the new configuration. And if not, I reject it. Now that's often the key piece in these multiple minimum search algorithms. And since beta is something like the temperature, or 1 over the temperature, then you can slowly lower the temperature, which makes these changes, the weight, the statistical weight of these changes greater. And in this fashion, you slowly converge in on the global minimum, because you spend most time there. What I haven't said, but the nice thing about this Metropolis algorithm, of which this is the key step, it is what is called, it does what is called preferential sampling. So it samples the configuration, it samples phase space mostly where it's important. In this case, it would mean it spends a lot of time here where the deepest minimum is, and less time maybe where the minimum isn't as deep. Depending, of course, on temperature, because temperature, it also contains entropy, of course, and a finite temperature, it also acts according to entropy. It's not a procedure per se to look for the minimum in the potential energy. It only does that in the limit that the temperature goes to 0. So this is why you need these relative artificial cooling schedules, where people say, okay, I first go and look, at some elevated temperature where there are points of special interest, and then if I notice there's something here, I slowly cool down and work my way into this minimum. So this is what can be done. It's a very robust algorithm to do this, and I would suggest this for somebody who's doing, for instance, protein conformation analysis as well. There are other ways of doing it, like genetic algorithms. And I actually, unfortunately, this is only in German, but on my home page, you find a rather substantial set of lecture notes, 600 pages. It's a book on, it's a lecture note on molecular modeling, and molecular modeling of force fields is on a page which you find on Constanze, named materials. Uni, Wuppertal. Unfortunately, it's in German, but lots of formulas in there, so you can maybe even get something out of it without the German. And I discussed a number of methods to solve this multiple minimum problem.
Are genetic algorithms more prevalent than?
No, definitely not, in my opinion. I mean, the point is I've played a lot with these genetic algorithms, and I was always kind of disappointed because, depending on how you define these various pieces that you need, mutation, crossover, and so on and so forth, you get something. But usually it's not that reliable. You easily get stuck someplace and then you are idling there. my preference really is the Monte Carlo method. I think it's the most robust method. This guy Shiraga, actually, I was mentioning before, he had a very clever idea at the time. He said, okay, if I look at something like an energy landscape like this, yeah, I pretend this is really something like ink. Yeah? Let's say you had an ink drop in water, and for some reason, if you cut through this drop of ink, it may have such a concentration distribution across the drop at this particular point in time. Then you would expect diffusion to smear this out. Yeah? So the white curve would actually become wider. Yeah? Then the minima would become less steep. Yeah? Over time, the maxima would become less steep over time, and so on. And you could continue this. Yeah? So as there's more and more diffusion going on, now what you finally find is that only the deepest spot here remains. So you would have to go, in the end, after enough diffusion of your original potential energy, it's not ink which is diffusing, there's potential energy, you go and just look for the single minimum it still contains. And then you get yourself attached to this minimum and you do the whole transformation in reverse direction. So you go from here to here, and finally, after you reverse everything, you find the true global minimum of your problem. It was called the diffusion equation approach. It was very nice. I played with this for some time, and if you look in the literature under this diffusion equation approach, you will find how this is done. This is basically the diffusion equation, the real diffusion equation applied to the potential energy. Yeah? With some tricks, you basically smear the original potential energy out so that it becomes more smooth in various transformation steps, and then finally you can easily find the only remaining minimum in this function and basically trace it back to the minimum, the global minimum of the original function. That was an idea, and you can use this for protein folding, but I don't think there's any particular exceptional way to do this. You know? It's also, I think it's still a very complicated problem. It has been solved for certain really small things, but as I was saying this morning, proteins are often relatively highly charged things. So these partial charges are relatively large. They also may vary because there's polarization going on. Depending on the shape, you may have a lot of electrostatic interaction, and that's the real difficult part in these potentials. And there's not really a very, very good way to calculate the electrostatics correctly, except if you do a high power quantum chemical calculation, which you can usually not do for these large objects. Yeah. So there's still some work to do, I believe. More questions?
Professor, to solve this molecular dynamic problem, we use the MS.
Yeah.
Is there in advanced modeling need for more powered, more efficient, more precise numerical schemes, or the literature is so wide that if you need any of them, you just look into the literature and find someone suitable?
If you feel the need for something more precise, yes, I mean, there are certain, I mean, of course, there's a whole bunch of these integrators. You can have, I mean, people using gear corrector, predictor corrector methods of various order. You could also think about more complicated things, but you always have to consider in this Valais scheme, we only had basically one force calculation per step. Yeah? And if you increase that, then you increase your computational effort quite a bit. And some of the more complicated schemes would require this. Yeah? And so the question is really, would you get something out of it? I mean, just by the, just if you just look what people have used over the years, over the decades almost. I mean, Verlet, that was 1970s, really. And so there's 40 years of simulation now, and these schemes are still around, are still very much in use. It's just an evolutionary thing. You're still very good. They still do a very good service, and nobody has really come up for general molecular dynamics and said, no, you can't use that, it's not good, there's something much better here. They're just simple, relatively precise. If you need some more precision, you decrease the integration time step, yeah? And that is as good as anything and better than most. Yeah?
So it's better to focus on speed rather than higher precision. That is not really.
I think it's better to focus on speed. I mean, what precision really means is also a question. If you model something like this, and you have these little hydrogens, and they may vibrate. Yeah? It doesn't really matter, really, over the long run, whether, I mean, you follow the motion of this hydrogen atom exactly. Since your force field is a classical force field in the first place, it also contains errors just to the quantum nature of this hydrogen atom. Yeah, so you're trying to be precise in a place maybe where no precision is possible. And also the general shape of the molecule doesn't care whether, if you look at a particular instant of time, this hydrogen atom has moved, I mean, a couple of picometers to the left or to the right. Yeah? So it may not be really an advantage to follow the motion all that accurately. Yeah? Basically, as long as your simulation algorithm is stable and conserves energy reasonably well, you're okay. Yeah? The exact position of every single atom within a very narrow range is of no particular value in most of the cases. Yeah? Now this, by the way, is polyisoprene here, the stuff which is natural rubber. Well, synthetic rubber as well. You can make this synthetically, but it's actually funny because you know Edison, Albert Edison, the guy who invented the light bulb. He actually was also concerned about rubber. He was a good friend of Henry Ford and Harvey Firestone, and they wanted to make the US independent of natural rubber. Even today, you cannot make a tire, well, you would not make a tire completely without natural rubber. Natural rubber, the rubber that you get from the rubber tree, from the latex juice of the rubber tree, is far superior to its synthetic counterpart in various respects. And that's because of a lot of proteins, probably, in the natural rubber. Say when you try to tear natural rubber, it's much more resistant than synthetic polyisoprene. But anyway, this is a little piece of polyisoprene. You cannot recognize whether it's synthetic or natural. And what did I want to say? One thing I wanted to point out previously was when you rotate around a bond, this is what I meant. I mean, this piece of the molecule, it makes a large circle, and it would hit immediately some other molecules around. So when you do a Monte Carlo on something like this, you have to try to make other types of moves, crankshaft moves, where a whole group moves in a way so that the rest of the molecule stays basically put, which is sometimes difficult to do. Yeah, there was something else I wanted to say. Yeah, more questions.
Just on the temperature method, are there any other methods actually?
Oh yeah, a whole bunch of methods. If again, in this thing here, I have listed a number of these methods.
Yeah, okay, it's also just the case of thermodynamic equilibrium, because sometimes you want to also it could also be interesting to actually have an oscillation between two thermodynamic states where you would have a non-equilibrium in between, so to say. That if you, for example, model a chaotic system, are there any methods for that actually? Or
chaotic system, you always modeling chaotic system. If it's not chaotic, then it's not good for what you are trying to do.
and then eventually you reach if you reach equilibrium, you sort of have a steady state, whereas you could technically also have a transition between two steady states, which depends on.
Well, make an example. What would you want to do?
Well, yeah, okay. I just would more or less remember it from the Belousov reactions, for example.
Yeah, Belousov-Sabaczynski oscillating reactions. Well, that's of course non-equilibrium thermodynamics essentially, and I don't know whether actually somebody has tried to model something like this with simulations. I don't think that would be very useful. What people, of course, study are coupled non-linear chemical equations and want to involve this. There are models for this, as what is called the Bray reaction, or some other models that basically show this oscillating behavior. So you have a number of coupled differential equations when you look at a particular solution, and you see this oscillation, and people have basically tried to model these chemical reactions. But you would do this more or less, well, if not analytically, but certainly not with these molecular models. Yeah. But there are non-equilibrium problems which you might want to address with molecular dynamics, like there are people who study transport coefficients, like the diffusion that we were talking about, or conduction of heat, or some just mass diffusion, conduction of heat, diffusion. What else do we have? And maybe coupling between these coefficients in terms of non-equilibrium molecular dynamics simulation. I had no time to talk about this. What you basically do is you set up a system that is not uniform. So it may have one temperature on one side and another temperature on the other side of the box. And then the particles move according to this temperature gradient. People have developed techniques for this to get out reasonable numbers, but there are, in my opinion, good approaches for these things that you can carry out in equilibrium, where you are always a bit on the safe side. Like the relation I was showing to you, the Einstein relation for the diffusion coefficient, there is another relation, which is what is called a Green-Kubo relation. It calculates the diffusion coefficient on the basis of the velocity-velocity autocorrelation function. And you can do this for other transport coefficient as well. In the case of the thermal conductivity, you would investigate an energy autocorrelation function. So how is energy transported in the system? It's different from, for instance, mass. If you transport mass, this particle has to actually move from here to there. If you want to transport energy, you can transport it directly with a particle in terms of the particle's momentum, for instance. But you can also have a process where this particle hits another one and that hits one and so on. So it's basically then two types of diffusive processes intermingled, and you can handle this as well with this appropriate Green-Kubo relation. And there are Green-Kubo relations for conductivity, electrical current conductivity, and other transport coefficients as well. And I would actually most of the time suggest these methods for transport coefficients, and that can be done in equilibrium. More questions? Okay. Yeah, I wanted to, maybe if there are no more questions, or if you think, oh, actually, what this is. My intention was to bring the sheets with the problem and distribute it. And then I must have left it in my office. Well, you all know what the problem is, and I can give you my email address before we get that too. It's my last name, except my true last name has an E at the end, so it's HENTSCHK, and then it's at Wuppertal. So what you can do is, when you complete your homework problem, I don't know, I have not really talked to the organizers about this, what kind of grade you are supposed to receive and how the grading is supposed to be done. But in case you need a grade, then you can hand it this homework problem to me. You should, of course, not forget your name. And I will look at it and then assign a grade and pass it on to Professor Henchel. That hand-in should include your program, hopefully not too long. And it also should include a number for the diffusion coefficient. Or maybe you have done this calculation a number of times, then you have several numbers. I would like to see those too. Okay. Actually, I wanted to give you an idea of, let me ask you, who of you wants to stay in academia later on, and who of you wants to go to industry? Nobody wants to go to industry.
That's a difficult question.
Huh?
That's a really difficult question.
Why is it difficult?
For instance, I still don't know exactly if I want to stay in academia or in the industry. Both sides are quite interesting. Both sides have pros and cons. And
one is the starving side, and the other one is the good side. You can guess which is the starving side.
I'm thinking either master's or beginners in PhD studies. Are you some people who are in the end of PhD?
I don't know. Who is actually a PhD student here? So you should know what you want to be. Where you want to be in 5 years. You don't know. Actually, I thought so long and so hard about this until finally industry said they didn't want me anymore. And then I had to hang on and hope for the best, which today I wouldn't do. If I had to do the same thing again, I wouldn't do it like this.
What would you recommend?
Yeah, you should certainly look into industry. I mean, the point is, I mean, you get done with your PhD. So then you say, okay, I want to stay in academia. So most likely, the next thing you do is you try to get a postdoc position someplace. That means long hours, hard work, little pay, and an uncertain future.
Sounds really amazing.
I remember taking my first postdoc position, and there was this lady professor who I was then working for, and she said, well, I expect you to be in the lab at least a couple of nights, and she meant really overnight, because that's what you're supposed to do as a postdoc. You spend your nights at the lab working on problems. I don't know. I did that, and then it got stuck, and of course, I mean, often enough, I ended up with somebody else, also postdoc. We would look at our wristwatch. It would be early in the morning, and we would be doing research, which is kind of crazy if you think about it. So then you get done with your postdoc, and what do you do next? You apply for a university position, maybe. So maybe there are 2 positions available for you every year, and maybe, huh? The what?
No, the whole world.
The whole world. Yeah. Yeah, okay, there are 2 positions in the whole world. That makes it even more attractive. And then there are maybe 20 other people who want the same 2 positions. So they're all roughly equally good. And then statistically, you have a chance of 1 out of 10 to make it. So you can calculate the probability to be 50% for getting a job. How many years does that take? Yeah, it's quite funny, actually. I don't want to discourage you, by no means. But if you really think about it, it's kind of a tough situation. I've seen people who were really, really good. I mean, there was this one guy I once met. He could solve any problem in Jackson electrodynamics, no matter which problem you point to within a minute. He knew this all, and other books as well. Last thing I heard from him that he was building canoes in Maine in the US. Canoe, about a canoe.
Ah, okay.
There was a canoe builder in the end. Boat builder, right? Boat builder. Which is not bad. I mean, it's a nice occupation. So industry is something you should definitely not scratch off your list, especially since, at least in Germany, that would be true. I'm not exactly sure about other countries, but in Germany, it's relatively, I wouldn't call it easy, but certainly not more difficult than doing it any other way, to go from a position at industry back into academia. That has been favored in recent years. So you spend a few years in a research department in an industry, and then you apply for a position at a university that may very well work out for you. And of course, in the meantime, you had a much higher pay. So
It's important for everyone to have children, wife, and so on.
yeah, sure. I mean, by the time you have children, the children want a new smartphone, and then they want an Xbox, and they come home and say, well, we are going on a trip to Paris. It's only 300 euros. It's dirt cheap. Yeah, of course, you must think about that. It's difficult. And something else you shouldn't forget about. I mean, last week I was at a meeting and I met a woman professor. She's originally from Italy, from Genoa, and is now working in Great Britain. She's an only child. Her parents in Genoa are getting old, and she doesn't find a position in Genoa, but in Great Britain. And now she's worried what happens to her parents. All these parents spend a lot of effort. Our kid has to go and get a good education, university, and there are two positions. One in New Zealand and the other one in I don't know where. And that's it. So this is something also to consider. If you work for industry, there's usually something close by. For instance, if you go into the tire industry, chemical industry, let's say, there are good jobs for people who do theory, like as I was saying, tire industry, they have research departments where they ask people to find out about friction and improving rolling resistance. And you may say this is boring, but it depends how you look at it. And I've seen people spending some years at this industry, then moving up within the ranks. I mean, there's the guy who is much younger than me, but when we meet in the parking lot, his car is 2 meters longer than mine. And his salary is probably double of what I have. Yeah? And there's another guy who worked for the same industry. He became a professor, and so he switched back from industry into academia. That's not bad at all. But they ask you tough questions at industry. So this is why I'm holding these two rubber balls here. So if you drop this one, you drop this one, I do the same actually. But I had a third one. Oh, yeah. So look all the same, all yellow, same size. This one is bouncy, and this one is not. You can look at them, feel them, and feel whether they feel any different. So if you want a job at this industry, you have to answer why is one bouncy and the other is not. You know that?
One is from vulcanized rubber, one is from natural one?
No, well, actually, vulcanization is a general process. Does anybody know what vulcanization actually is?
Basically, the heating process with sulfur.
Right, yeah. You want to cross-link. I mean, if you just have unvulcanized rubber, it's still rubbery, yeah, but it's not as tough as vulcanized rubber. And what you do is you construct basically sulfur bridges between the individual polymer chains, and this makes this material really tough and elastic at the same time. No, but they are all vulcanized, both types.
Definitely with shocks. Basically, if you drop the reaction in the surface to the rubber, would make them react differently. So it depends how hard you hit it. If you hit them slowly.
That's an observation, but that's not the explanation. That's the observation which you're supposed to explain.
Okay.
Now you see where the trick is, right?
Yeah, there are lots of people in this world actually doing computer simulation on these polymer systems. That's a loving topic. So if you say, before I came to Wuppertal, I was at a place that is called the Max Planck Institute for Polymer Research. And you can apply there to do molecular simulations in polymers. And then, say you spend there a year or two as a postdoc, and then you apply to the rubber industry, you solve this problem, and you go on buying a big car and earning a big salary, and 5 years later you say, oh, go back to the university, and then you go back to the university.
I have a second. So,
yeah, okay.
the polymer molecules are not radially distributed in one
Not really. It would be tough not to do that. I mean, the polymer molecules are really hard to control individually. No, what this is, I mean, you were basically going in the right direction. Rubber is a very complicated material, and depending on, for instance, the cross-link density, you can put in more or less sulfur. The frequency response of the rubber will change. If you have something like, when the degree of cross-linking is relatively low, it's more flowing, and you can, I mean, there are more degrees of freedom in a certain sense, and it's can respond, I mean, to certain frequencies more easy than something that has a higher degree of cross-linking. And of course, if you want to build a tire, you have to control both aspects. If the tire is real bouncy, your loss is small. Bouncy means that the energy is stored and then released again, and stored and released again. And so that is a nice tire if you go on a straight autobahn and you want to consume little fuel, you want the tire to be bouncy. But when you brake, then you want something else. Or if you drive around a corner, you want a good grip, and you don't want this thing to be bouncy and slip off the road. So people in the tire industry, for instance, may approach you as somebody who's doing molecular modeling and say, okay, what can you do for us? That's a typical question that you might face when you go and apply to industry. We have done some molecular modeling at a university or institute, and then you go to the industry and they listen to what you have to say. You usually tell them something about your thesis project, or maybe something about your PhD project, and then maybe something about what you have been doing as a postdoc. You say, okay, I'm doing simulations, and then they say, oh, well, if you do simulations, we have this department, and there will be probably somebody sitting there from that department, and then they say, okay, we are interested in reducing the rolling resistance of a tire, and you could help us to think about this and do computer simulations on this. And then you suddenly notice that the tire is this big, and molecules by comparison are very small. Now you can think about it, if the tire was the entire circumference, as big as the entire Earth, then the molecules that determine much of the rolling resistance are like grass. This is a complete nonsensical ratio. The rubber here, not this one, but the tire rubber, is filled with tiny particles, and in order to make these particles compatible with the rubber, they have to be coated. It's like grass growing on these tiny particles, and the size of these grass, the size of the grass or the height of the grass, as I said, if the entire tire was as big as the entire Earth, then it would be like grass in the streets, and a particle in a tire would be as big as a house, but that's tiny in comparison to the size of the Earth. So what you have to do if you're applying these modeling techniques to real environment, you often are faced with a problem to bridge the scales between something that's very tiny and something that's very large. And another problem is, of course, as I was saying before, there may be very long times in comparison to what you are modeling. So if somebody is testing rubber in a lab, they will probably push on it. There are machines that will basically twist the rubber, and they will twist the rubber with a frequency of maybe 1 Hertz. But when you do your computer simulation, you twist the rubber much faster. I can actually show you such a simulation that pictures that. See? A little movie here of somebody who's done this. Just very briefly, so that you know what's going on here. If you look into a tire, actually this is a tire. The funny thing is when we go and we tell industry that we want to give a talk someplace, I had a tire here and told me I have to take the tire away because I'm betraying a secret if this was a tire. So I had to put this blob as a cylinder. This is a tire. If you cut the tire, little piece of rubber off the tire, and you look at it very closely, then it looks roughly like this. You see something that is lighter and these dark patches here. And the dark patches are actually little particles, nanoparticles. There's here an actual picture of something like this. These tiny particles form larger aggregates. And these aggregates again form larger structures, and in reality it looks more or less like this cartoon here, and what is the light patches in between would be rubber. And you can make very thin slices and look at them under an electron microscope, and then it looks like this here. But this is for a relatively small filling. So these particles are called filler, and they produce the strength of the tire. Without the filler, you couldn't really use the rubber as a tire material. And so what you want to study is what is this filler network you're doing inside the rubber as it's basically twisted around. So if you approach a problem like this, it's good if you have a lot of knowledge of other things as well. Some people do say that these networks formed by the filler are fractals. So you should know something about fractals. And what is a fractal geometry? What is fractal dimension? How do you determine fractal dimensions maybe? Also, in order to talk to the chemist in a company, you should know something about chemistry. So if somebody tells you, okay, this is polyisoprene, then you should know this is polyisoprene. Or something say, this is styrene butadiene rubber, then you should know what that is. So you need some chemistry as well. You also need surface physics. You have to know what a surface tension is and how you measure surface tensions. You need to know something about absorption on surfaces, because there is here a contact between the rubber here and the particles there. This interface is important. You need to know something about this, and of course you need to know something about molecular simulations as well. Oops. And then you have to decide to construct a model. And one model that we had constructed that looks like this here. So that would be our version of such a filler network. The colored spheres which you see here correspond to the smallest particles in the simulation. The smallest particles in the filler. The smallest particle in these filler materials are not really small. They are not molecules. They are quite a bit bigger than molecules. They are about 10 to 50 nanometers in diameter, or maybe 100 nanometers even in some cases. In our case, they are monodispersed. That means we only have one size, and this is the smallest thing. So it's a lot bigger, actually, as a molecule. You notice something. We have already gone away from the molecules to much higher, much larger entities. Also, you don't see any polymer here. The polymer is gone. The polymer is substituted by little dots. You see these little dots. And actually, these little dots are like crosslinks, and you don't see the polymer. The polymer are springs between these little dots. So we have substituted the polymer by a network of strings. this is not really science anymore. This is a bit of an art, because you have to decide at some point, as somebody who's doing modeling, I cannot do this on the level of the molecules. I have to do it on a higher level, and you have to construct alternative models on a different scale. And then you have to try to capture the essence of the material. Sometimes it works and sometimes it doesn't. So we have tried to capture the essence of the material on this level here, and then we can push on it. Yeah? So if the machine with the rubber sample is twisting the rubber sample, so are we. We are twisting the rubber sample here. That is basically the bottom is sliding this way, whereas the top is sliding in the opposite direction. So it's kind of a sharing motion here. And the flickering balls, which you see every now and then, that's again due to the periodic boundary conditions. Yeah? The motion may push one of those little particles across the boundary, and then the program is set up to immediately show it on the other side. And this is why you sometimes see a little particle disappear on one side and reappear on the other side. The small particles are substitute for the polymer. Yeah, there is in the normal sample, this is a filler network. This is like sand, basically, little grains, and they are thrown into a mixer which contains polymer. And the polymer is not shown here. The polymer is not really in the simulation explicitly at all. The polymer is basically just represented by its elastic, linear elastic properties, more or less, by saying, okay, we put in little nodes and we connect these little nodes with springs. Yeah? So you have basically an elastic network, which is enclosing all of this and holding everything together. So this whole system consists of a network of springs, where the springs are not shown in this picture, only the points where the springs attached to, plus these aggregates. So balls of the same color form an aggregate, and then these aggregates can interact with one another, and the aggregates are also connected to these springs here. And so all in all, everything is basically connected to everything else, but just with short range forces. And we can push on this and conduct basically mechanical measurements. And what these people are interested in, I can show you this as well. I'll go back to this top here. This is what the industry here is interested in. What is shown here is a storage modulus. I'm not sure whether you know what a storage modulus is.
You asked us a question that we should get what happens to this. And maybe there's not just outside friction, but inside also. So there is energy. So when the ball bounces, and it doesn't have much reaction inside, then not much energy gets lost. When it bounces, and it can go up very much. But if it loses much energy inside by friction,
right?
Because the molecules inside of by friction, then it loses energy.
No, this is exactly right. I mean, the contact between the ball and the table surface does not create much loss. It's the deformation of this ball as a whole, that is responsible for this. And this is actually
in the simulation. How can I describe this in the simulation?
I go back to my this is actually in this picture here. This is what we're talking about. We are looking inside the material, and the material is characterized by a quantity which is called the storage modulus. You may, to some extent, at least here, there's another axis here which is called strain. Strain is basically how far you pull this. Now, how far it's basically a measure for the deformation. It's a relative deformation. That's what strain is. So if you have a small strain here, there are various curves here. Let's focus just on the blue one. If you have a small strain, this is in percent. This is only around less than 1% strain. So if you have something that is 1 meter long and you apply 1% strain, then after it has 1 meter plus this 1% strain means it's 1 meter and 10 centimeters long. So it's a relatively small strain here, and you get something like this number here for what is called the storage modulus. And you might say that the storage modulus is a little bit like a spring constant. At this small strain, it's a spring constant, but the spring constant in this material is not a constant anymore. As you increase the strain, the spring constants get weaker. Normally, if you have a spring, ideally in physics, the spring constant does not depend on the amplitude. You don't want this. But this spring constant does depend on the amplitude. And this is because what happens, is that when you pull on this stuff, the little contacts here between these balls, which you see here as dark circles, the contacts are broken. So there are little cracks appearing in the material, and that weakens the material and diminishes the spring constant. And this is what we have tried to model here. So we made models where we have some mock aggregate and another mock aggregate, and there's a contact here. The contact is between these two dark balls interacting, and the gray shaded area here at the bottom and here at the top, this is rubber. So it's a primitive model of a rubber link in the network, and the rubber acts like a spring trying to hold these two pieces together, and there is another piece of interaction in here, and we can pull on that and study basically what happens. And this kind of breaking of contact, where these two pieces are pulled apart, that is the internal friction that you were mentioning. So this is actually internal friction that leads to the decrease of the spring constant. And unfortunately, that decrease is not coming back when the strain is released. But it is dissipated. This energy is then dissipated, and there's another quantity called loss modulus. It describes basically the dissipated energy in a certain strain cycle. And here, where the loss of the spring constant is highest, we also have a high loss really on the other side. And this is internal friction. So when your tire on your car is turning, it is deformed and it's losing energy. It gets warm. When you touch it, it gets warm. And when you drive for a long distance, it gets really hot sometimes. And this is the kind of friction for which you pay a considerable amount of money, because this is really just money burned basically on the street, and you can't change it. So, in other words, if you go on a long trip, you should always check your tire pressure, because if your tire pressure is too low, and your tire gets deformed, if your tire gets deformed, it gets hot. It's your money which you burn on a trip like this. On the other hand, if you overfill your tire, say it says 2.5 bar in the description, and you fill it to 3.5, you save money. There's no special thing about the tire pressure. I asked the guy who's designing tires, I said, well, why does my manual say 2.2 bars? And I said, there's some commission someplace which decides this, but if I put in 3.5, it's also all right. I put in 3.5, I save some money because the tire gets less deformed, and I save some money. On the other hand, I have to say that if you overfill the tire and you come into a dangerous situation, you may also lose some contact with the road. So you have to take that into account as well. It may become too bouncy, the whole thing. So, but there's nothing magic about putting 2.5 bars in your tires, or 2.6 or 2.7. You had a question?
If we spring here break it, so that my tire is much of its material on the street?
Well, it's a good question. Let me think about this. How long does a tire last? How many kilometers? Have you never bought a tire? Huh? That's another thing you have to buy from your measly postdoc salary. If you buy a good tire, it's expensive. No, a tire lasts for about, I would say, depending on how daring you are, 40,000 kilometers. If you calculate, I mean, the thickness that is worn off is about not quite a centimeter, I would say. It's maybe 6 or 7 millimeters. You can calculate if you have 40,000 kilometers turning tire, how much you would drop off on average during these 40,000 kilometers per turn of the tire. It's tiny. It's really just it's basically the thickness of a molecule. But unfortunately, it's not so that the molecules abrasion on a tire is not that you every time the tire is turning, you basically lose one thickness of this molecule which then sticks to the road. That isn't how it happens. It's a bit more like an eraser. When you rub an eraser on a piece of paper, you see these little flakes, and that's similar with the tire. But sometimes, depends on the driving conditions, there's almost no loss if you're on a dry road or maybe also on a wet road, and you are not exerting much of a shear force on the tire. It's just rolling along nicely. And there's little loss, and there's maybe a little bit due to heating, and then to degradation of bonds of the polymers, and maybe some stuff is sticking to the road, but that's very minute. You lose most of the material in particular situations when you have to go around a corner and brake very sharply or accelerate a lot, stuff like this. That makes it acceleration, deceleration, and this is where you lose most of the material. And the way it works, it's a little bit like an eraser.
You showed us those two different balls, and one is very bouncy.
Yeah.
So one would like this for the tires.
Well, it depends on the situation you're in. That's the art of tire making. If you are just going straight on the autobahn, this is what you want, the bouncy one. It loses little energy, everything is fine. But if you come to a situation where you have to brake very sharply, you invoke a lot of frequencies, also high ones, and then suddenly the contact to the road is lost because it's very bouncy and loses contact to the road, and you don't want that. In this case, you would rather be happy with the other ball, which is basically dissipating a lot of energy in its interior, and it sticks to the surface without bouncing back. And this is the art of tire engineering. You have to find material combinations for the different driving conditions, which are at an optimal.
I have a question.
Yeah.
Some materials change their properties when you turn on the. What about like you have continuity with tire? You turn on the people. Yeah, why not?
Well, the first thing the tire people ask you is, what does it cost? And that would certainly cost too much. You're right. I mean, there are materials where you can control material properties by turning on electric fields. I mean, if I look at an LCD screen or something, that's a good example. But you wouldn't want to change tire properties by turning on electrical fields. This is not what you do. Whatever you do for industry, when you do your modeling, they tell you what does it cost, and you also have to be cheap. Well, I see there are not really that many enthusiastic industry people here.
But when I'm working in the industry, then I have enough money. And I can buy such expensive tires.
Maybe you could, but then you probably want to buy other things as well. But in principle, I mean, the tire industry is only one industry. Actually, some number of years ago, I wouldn't even have considered the tire industry. I wasn't really aware of the tire industry. The funny thing is, maybe if I can find this quickly, as somebody who started for the tire industry, and I show you a talk that he once gave to a general audience, more or less. This is a guy working for the tire industry here. Yeah? He was an engineer in the tire industry. Yeah? This is what he's doing. You know what this is? Recognize this stuff here? Yeah, right. Yeah? So then you don't have to throw all your beloved theory away when you go into industry. Now you can continue with this. Yeah? So you can solve Feynman path integrals. I spent many years in the tire industry to deal with things like this and this and so on. Yeah, think about polymers and entanglements and road conditions, yeah, and cheese and path integrals. Yeah, so that's about funny Hamiltonians. You can combine all these things. You don't have to leave that alone. I mean, if you're fond of this, I mean, you can do it. I mean, this guy worked for, I think, 10 years for the Continental company, and then he became a professor at an institute in Dresden. He has written a lot of books and papers and became famous with this, and now he's, I think, retired. So I think he's a good example for considering industry as an alternative if you want to do science. You should, I mean, consider that. I mean, if you go into industry, you also have a nice opportunity. You can decide. You can say, okay, I want to continue science. I want to become an expert. Yeah, then you are the person who they come to when they say, okay, our tires in China are losing their thread cap within the first 3 days. What thread cap within the first 3 days? What are we going to do? So you have to be the person who is technically responsible for the technical things, or you can say, okay, this is not what I want to do. You can go into the administration, into the management, and then move up usually. Of course, I mean, there are less positions available as one goes to the top as everywhere, but nevertheless, you can do this. And if you work as an expert, yeah, you deal maybe not so openly, because if the COAs come to your office, well, you will have to come to them. But anyway, you have to tell them something, and if you show slides like this, they may not be as happy. But you can keep this up and then go back to university and say, okay, I applied for a position at a university. And it's convenient, because if you only have 2 jobs every year coming up, yeah, and you stay at industry and you can apply, I mean, to a job every year, it doesn't cost you much. You just take a day or 2 off from your industry position. And in the meantime, you don't have to starve. You're getting a lot of money in industry, and if the university job works out, then you change over to the university. So.
Professor, are there many jobs in industry that deal with knowledge?
Yeah, I would say so. I mean, there are many industries. Like, I mean, if we take a look around, I mean, like in Wuppertal, you have, for instance, the Bayer company. There are people doing molecular simulation at Bayer. I mean, this is pharmaceutical stuff, and that was probably the first industry that was really working a lot with this kind of simulation, so with molecular simulation, because they usually deal in relatively small molecules, and there were some classical questions like, I mean, some enzyme that would fit into a certain pocket, yeah, of another molecule, and how they would interact, things like this. And so a pharmaceutical company is a good place to look at. There are other companies, like if you go to Düsseldorf from here, there's Henchel. Henchel is producing glue, it's producing beauty chemicals, beauty stuff, it's producing washing detergents. And I've worked with this washing detergent guys. They say, okay, we sell this washing detergent and we want to make sure it's well dispersed in the washing machine. I know this from my own experience. There's this, there's a big bucket with washing detergent, and you just grab something, a glass or something you find, or a spoon, and you dig into this and you dump it in your washing machine. You don't really read the prescription. It says maybe put in a teaspoon, but you don't put in a teaspoon, you put in a glass because you don't want to read the description. So they say people don't read these descriptions, they just dump in the washing detergent, and then we have to make sure that it works over a wide range of concentrations. And we want to make sure, for instance, that it doesn't form any type of water phase, for instance. I'll show you something that we have done for them. Wait, quickly. Oops.
How is it possible to make publications when you're working in industry? Because stuff you make there, probably they don't want to show to other companies.
That's a very good question, actually. I answered this question right away. I just want to show you something. That's the washing detergent. I come close to this. So there it is. Can I close it somewhat? What you see here is basically a box, a big simulation box with particles inside, and how do these particles look like? Let me show you. This is what they look like, really. So you have different. This is a molecule. These three guys are a molecule. It's an effective molecule. It doesn't exist in nature. Each of these beads here is representing a larger piece of a real molecule, and this is a head group of an amphiphilic molecule, and these are tail groups, and this is like water here. And so what we see later on is a mixture of where you have these molecules here with the head group and the tail group and water, and they form a particular phase. And the industry was interested in finding out what kind of phases they would get depending on certain thermodynamic conditions. And so we start a simulation from a more or less random arrangement of these molecules down here. And then after a while, we see these sponge-like phases, and you can change concentration and find other phases as well. I'm not sure whether there's another phase here. No, I don't have another phase here. But anyway, they were interested in getting these phase diagrams. If you want to publish in industry, of course, what you say is true. They want to keep things rather secret. It depends a little bit. Usually, it works. The guy I was mentioning before, whose talk I was showing to you, he has published a lot. It depends how well you know the guys in charge. If you know them fairly well and you can convince them that what you are publishing is not betraying any of the most recent developments of the company, then it's usually not a problem. All it will do, in essence, it will delay your publication somewhat. On the other hand, I think if a publication is something worth today, but is nothing worth in a year from now, that's probably not a good publication. So a good publication should also have some lasting value, I think. Anyway, in the case of this guy, it was certainly the case that his publications had lasting values. So Henchel here, other industries are chemical industry, like here in Marl, which is not far away, or Essen, Evonik is a chemical company. They make, for instance, silica. Silica is a filler which you put into rubber. You put it also into toothpaste. You put it into food. You put it almost everywhere. You know? So you can work for these companies because they say, okay, we need filler not for food. We need filler for maybe concrete, and we want to mix it into concrete. What type of molecule do we have to use to coat the surfaces of our filler particles so that the mixing is dispersing the particles really well? And you could work on something like this. So there are many places where you go up south to Ludwigshafen. There's a big company. They also do molecular modeling like the BASF. Yeah? You can do lots of things for the BASF. You can work on paints, you can work on glues, you can work on washing detergents as well. Lots of basic chemicals come from there and they want to know something about them. So there are jobs in these industries as well. I think there are more jobs for physicists in the chemical industry than in the physics industry because there is no physics industry in that sense. When I was a student, it was Siemens for us. We all want to, or at least some of us wanted to go to Siemens, and Siemens at the time was into magnetic storage and yeah, basically making tapes. Nobody's using tapes anymore. So Siemens is actually kind of out of business as far as jobs for physicists are concerned. I think you should really go and keep an open eye on the chemical industry. Chemical industry is using a lot of simulations. If you ever have the chance, I don't know whether this is taught in this school. Who of you has taken a course on finite elements already? Yeah, those of you who haven't should consider that. Finite element method is probably the most prominent modeling method in industry. There's no industry where finite element method is not the #1, except maybe for the pharmaceutical industry. But other industry always favor finite element modeling because it can really be applied to macroscopic systems. It's also in the tire industry, it's the method of choice. I mean, when they want to model an entire tire, they use the finite element method. So there are many, many jobs in industry. I can only recommend that. Yeah? Yes, that's also possible. We had a number of PhDs in industry. For instance, some time ago, I was on a committee of a guy who was actually working for Siemens. And he was a chemist. And Siemens at the time was in the business of harvesting light, not in photovoltaics, but they had this project which was called Desert Tech, and they were building large fields of solar power collectors, of collectors of sunlight. These are just mirrors, and they heat up what is called a heat transfer fluid. And the heat transfer fluid is, as the name is basically expressing, it's transferring heat to some heat exchange device, and the heat is converted into electricity, and then the electricity was supposed to be transported to other countries. And these heat transfer fluids have to fulfill certain requirements. They also have to be cheap. They have to have a high heat capacity. They have to have a low vapor pressure and several other things. And he was working here with a chemist, and he was doing his PhD on a project where he was looking into various heat transfer fluids and how they would work in industry. So industry sometimes does that they say, okay, you can work for your PhD in a lab, and we are interested in this because this is our current business. Yes, there's no problem with that. Anything else? Yeah, if you have additional questions while you are here, you can always come and look for me. My office is 2 floors down. It's F1217. And I think I will be here most of the time during this week. So anytime you have a question, just step in and ask a question. Other than that, I would say I leave you alone, leave you with your decision to become an academician. You should really think about this hard and say, where do I want to be 3 years from now? What is my plan?
Professor, have you met anyone related to your background in mathematics or physics?
With background in mathematics, more than physics. Yeah, I mean, there are people like this. Industry is relatively open to this. I mean, actually, if you fail this test here at Continental, for instance, it doesn't mean that you don't get the job. They look for people who have a certain set of skills, of course, but they in particular look for people who fit into the team, who have a quick mind, who can, where you get the impression during the interview that if this person is confronted with a problem, then this person finds a decent approach to the problem. And if your background is in mathematics, it doesn't really matter. I mean, it may be a good thing. Maybe it's a problem. They have lots of problems that have to do with math. I mean, when they do this finite element modeling, I mean, there are tons of problems in this area where they want to make their algorithms maybe more efficient. But then if it turns out while you're working there, you get interested in other topics, you can move into these other departments, and maybe you can bring, I mean, your previous knowledge in math to bear in a chemical environment. I mean, there are questions related to chemistry, which can be answered with math. For instance, when I was at this company last week, they were telling me that they want to get into data mining. So they have all these tests. They make tons, I told you, they make tons of these samples. 15,000 every year, 250,000 tests. All these results get dumped into the computer. So most likely, they have all kinds of data there, which they don't benefit from because they just have no way of really extracting certain things. That's, I think, a good problem for a mathematician. I mean, you have to organize these data in a proper way so that you can select certain properties very quickly, combine them with other properties in a sensible way, and make a prediction for some new compound that they might want to try. So this is something that is really combining math and chemistry and just physics, and it could be a lot of fun actually to do this. It's not really dry matter because there's a lot of information in this data and nobody knows how to get it out. Okay, well, I hope you have fun for the rest of the week. I think this is last week. Next week is
no, will be here next week.
We're almost halfway, so.
okay.
Yeah.
If you want to see me for some reason, you will have to come this week because next week I'm not going to be here.
Thank you.
Tomorrow,
I have a program.
tomorrow, there will be lab laboratory.
I don't know. It doesn't say on my. What I have is to show you. This is the timetable I've got here. That's there's an ND lab here. I didn't see that.
Yeah, very funny.
Well, you haven't solved your problem yet, have you? Yeah, you should spend the time working on this problem. I think it's worth doing, and I want to see some numbers which you haven't delivered. So I won't be here. Yeah. So I think you should work on this problem if you haven't completed it. And as far as I'm concerned, nobody has handed in something, so you all must be still working on this. Yeah. But I will be in my office, so if you have a problem, just come and look for me in my office.
You're supposed to hand the code in.
Yeah, it would be good. I mean, if I have some grading to do, I should have a look at the code as well. But you should also, and that's the most important thing, include some numbers for this diffusion coefficient.
Yeah, sure.
Yeah, and not all the same numbers. Actually, you should. Everyone handing this in should at least produce 3 or 4 numbers. Because if I look at 3 or 4 numbers, I can tell whether the numbers are real. Yeah? There are certain ways of checking these things by just looking at the scale of the numbers. So not just one number, but say 3 or 4 different runs and different diffusion coefficients. Yeah.
The first thing is that you like it for some reason, just close. Yeah, well, that's the first problem. Then now I guess there's
that would be a little No, I see what you want because the code would take a while.
I will first try to just, yeah.